Objective of this experiment is to find the maximum shear strain, shear stresses, and modulus of rigidity. The second one is to obtain the relationship between torsional load and angle of twist for a full range of strain until failure. Additional theory. Torsion occurs when any shaft is subjected to a torque. The torque causes the shaft to twist. This makes one of the ends to rotate relative to the other. The shear stress is induced on any cross-section. Besides that, torsion testing is made on materials to determine the modulus of elasticity and shear, torsion yield strength, and the modulus of ruptures. The shearing stress at any point on a transverse cross-section varies directly proportional to the distance from the center of the shaft when a simple circular solid shaft is twisted. Therefore, during twisting, the cross-section is initially planar, remains a plane, and rotates only about the edges of the shaft.
For the calculation, firstly we have to find the formula. The first one is J, which is J is the polar moment of inertia, equal to pi d with the power of 4 divided by 32. The second one is shear stress, equal to Td over 2J, and the last one is shear strain, which is r theta divided by L, where D is diameter, T is torque, R is radius, theta is the angles in radians, and L is length. First thing first, we have to convert all the value from millimeter to meter. So here we've converted the diameter from 6 millimeter to 6 multiplied by 10 with the power of negative 3, and the radius, which is half from the diameter, so the diameter we divide by 2 and get 3 times 10 with the power of negative 3. To calculate the brush, we just have to substitute the value and we will get 5.89 multiplied by 10 with the power of negative 4. So since there are 14 readings in the first experiment for brass, I'll show 3 examples of how to calculate the shear stress for brass. Next one is how to calculate the shear strain for brass by using the formula shear strain equal to r theta over L. Firstly, we have to convert the angles from degree to radians. This is how we get 60 degree times by pi over 180, and we will get 1.047 radians. Then we just substitute the value into the formula. So the first reading we will get 0.042 for the shear strain. Since there are 14 readings, here I show you 3 examples how to calculate the strain for brass. The first one we will get 0.042, the second one we will get 0.084, and the third one we will get 0.127. As we finish with the brass calculation, we have to move with the Meister calculation by using the same formula. First, we have to convert the diameter from millimeter to meter, and we will get 5.96 times 10 with the power of negative 3 meter, and substitute the value into the polar moment of inertia formula, and we will get 5.85 times by 10 with the power of -4. Uh, there is only 4 readings for the mild steel experiment. So here I show you all the calculation. The first one, by substitute the value for shear stress, we will get the first readings 99.33 Newton per meter square, and the second one we will get 100.81, and the third one we will get 76.41, and the last one we will get 0.10. So here the last one calculation for this experiment, which is the shear strain calculation for mild steel. By using the formula, shear strain equal to R theta over L, and we substitute the value. For the first readings we will get 0.04, and the second one we will get 0.08, and the third one we will get 0.12, and the last one we will get 0.16. So here is the result we get from the experiment for brass and mild steel. Here is also the readings we get in the experiment for every 60-degree angles, and here is the readings we get for mild steel experiment for every 60-degree angles.
For the discussion, the first one is plot a graph of a shear stress against a shear strain. The first graph that shown is the brass, and the second one is a mild steel. The second one is determine the shear stress at the yield point. To get the shear stress, the formula is Tr per J. So the shear stress for the brass is 77.32. The shear stress for mild steel is 76.41. This is the specimen image after a failure for a mild steel and a brass. Based on the final length and diameter, show the effect of torsional stress. The diameter of the brass specimen shrank by 0.1 mm from its starting diameter, where the mild steel specimen shrank by 0.16 mm. As a result, we may deduce that this experiment will cause tension until diameter decrease.
For the conclusion, steel has the maximum value of modulus of rigidity and applied torque at failure, which means that it is stronger than brass. So it can withstand higher shear stresses than brass, and brass has the least value of angular displacement at the fracture. So this shows that it has lower ductility than steel. So that's all from me. Thank you.